everyone, how are you doing? That's one of our bunnies right there. That's Morty, but Jolly is Jolly's under the weather. So sorry for the little late start here. We got great questions in the chat, some 475 questions. Give the bunny some treats. He got some critical care. So I was syringe feeding him some critical care. So I'm just like, I had him towel wrapped. So I've got him in a towel and I'm holding him and he's just like, and I'm putting this, and he's just like, so he's eating his critical care. But good to see everyone here. Madeline, Abby, Andrew, Colton, Robbie, Thacker. Yeah, so he's being fed. So sorry for the little late start here, but the bunny needs some help. But it's Jolly. I don't have any pictures of Jolly on my phone. But I got lots of pictures of Morty. But Jolly's our little one-eyed rabbit. He was a surrender. So people couldn't take care of him. I syringe fed and raised a squirrel. It was interesting, yeah. So you probably towel wrapped him or something like that. But good to see her, Leo and Tessa. Yeah, you gotta kind of basically, you're just trying to help them, but they're a little bit confused as you're trying to like feed them, and they're like, "What is this? What are you doing?" And you're just like, "Eat. I'm going to give you food, and you will eat, because if you don't eat, that's bad. That's going to be another problem." So we're hoping he starts doing more bunny type things. He had one other episode a few months ago where he got a little bit didn't want to eat. So I've also syringe fed 7 baby possums at the clinic. That's awesome. Thank you, Tessa, for all your help right there. Syringe feeding is difficult, and that's why between classes I was literally just last 20-25 minutes I was syringe feeding. It's a slow process because you're giving him a little bit of food, and then you're like, okay, I'm just gonna let him chew on that food for a little bit here. He's like just chewing away. We rescued a baby bunny. Emilia's saying rescue baby that had one. Aw. Yeah, I mean, bunnies can get hurt in the wild. Bunnies will fight bunnies. Ooh, bunnies will fight bunnies. Ooh, bunnies will fight. Ooh, we're going to do a little 475 to start, but 201, what questions do you have? I think we're going to do a little 475 to start. I'm getting this loaded up right here, and thank you, everybody. Everybody is so awesome. I'm going to be checking the emails here in a moment, too. It is a busy day. It is a busy day. And let's go back over here, grabbing the assignment. Do a little 475. You have to go slow to not dry. Ooh. You're making me want to go check him. I'm missing the different shows into. Oh, thank you, Connor. Yeah, well, you can see all the different intros. You make me want to go check on him. I think I would have noticed if I did it. I did go slowly. He seemed to be fine. I was trying to feed him some parsley afterwards, and he was like, you fed me enough. Yeah, no, you gotta go slowly. I'm so afraid with bunnies, like I'm gonna hurt him. We got a few questions. 475, we got 3B and 2B and 2C. So let's talk a little 475 here to start. BAS 475, 2B, 2C, and 3B. So REMA models. Okay. Could you review over sampling distribution? You bet, Ford. We'll do some sampling distribution. Put the questions in the chat. Sampling distributions 201. Stat 201. Sampling test 2. Practice exam question 6, Leo says. Keep putting questions in the chat. I'm taking them down with your tongue right here. Practice exam 2, question 6. You bet, Leo. Decision trees. Would you say there's a lot of... I mean, there is some. Definitely no decision trees. They're pretty favorite of to break down the formula sheet. We could do that right here. We could do formula sheet. Stat 2, 1. Test 2. Formula sheet. We did it during the Kahoot. The Kahoot's a good spot for that. And decision trees, right? Let me put that down here. Okay, we're going to start here in just a second. Stat 2, decision trees. Oh, hey. Hey, everyone's here. Let's do this. Let's hop over and do some REMA models and check it out. So 201, stay tuned. We are going to go back to some 201 here in a moment. We're going to start with some BAS 475, probably for next 10-ish, 15-ish minutes, and some decision trees will be coming up. And if you are 201, hang out. You're going to hear some topics that are related to 201 probably. I'll try to weave in some, teaching to the test moments. And this is the 475 class. And let's take a look right here. We've got a series right here. It says that you are going to do some transformations of a series and differencing. For the following series, find the appropriate order of differencing after transforming it if necessary to obtain stationary data. So stationary data is basically random data. And in 201, we actually want to see that we have kind of randomness, and we talk about it in regression. Like I said, I'm going to weave in some topics right here. What condition do we look at for randomness, and where do we look at it for 201 in regression? Tessa, definitely we do some review of those. And for 201, when do we think about like these things should look kind of random? We talk about the what should look random. Like what here do I have on the screen should look random? What is this right here? What is this? QQ straight enough. No outliers. Plot doesn't thicken. The what plot? QQ straight enough. No outliers. Plot doesn't thicken. The what plot? The residual plot. Seth, you are correct. These topics carry over to every class I teach about residuals. Because if we look at this right here, let's go ahead, and I think we already supplied this code right here to grab a certain series, and let's plot the series. My series, and let's auto plot it right here. And here's the series. So this is the data we're looking at. Do you notice here there looks to be a linear trend in the data? There looks to be a linear trend. Now what we can actually do is we can go to TS residuals. Oh, do I not have Fable loaded up? So let's do this. TS residuals. GG, TS. There it is. GG, that one? There we go. What do you think these are right here? 475, if you're here right now, this is the what's of the model. This is the what's of the models. Just like in 201. Oh, we didn't show it for this one. 201, 475 crossover right here. That's just the what of your model. And look at the right there. What is residual on the exam? It's on this exam. Chapter 7 and 8 are on this exam. QQ straight enough, no outliers, plot doesn't thicken. Chapter 7 and 8 start. Those are the residuals, right? This is the leftover variation, just like that is the residuals. And so Colton, you should see right here, and Connor, great work, excellent work. These are the residuals. We're showing the crossover between 201, this plot right here, and this plot over here, which is showing us the leftover variation. Now, this C of the ACF stands for what, 475? This C of the ACF, the auto something function, stands for the what, which this value can range between -1 and 1, which we were talking about this at the very end of class today. That C of the ACF stands for the what? That C of the ACF. Yeah, you showed the GG, that, exactly. It stands for the correlation. That's the autocorrelation function. Auto means self. It's self-correlated. So at this point, everything in, we can probably do the GG TS. There we go. That's mad. It only gives us the TS display. So this is the autocorrelation function right here, and there's major problems. Major problems. And we should be able to pipe this into a differencing right here. Now, what we could do is we could look for the unit roots. That's good. Oh, she's happy about Akeka. She's looking to help out the bunny. That's Chelsea right there. We can look at the unit roots for this. Let me go get the FPP3 book, because I always forget how to do the feature on unit roots. So let's go grab the code right there to look for the unit roots for differencing. Unit roots. The book is so great. It's just like features, unit roots, stationary differencing. Here's the code right here. They're already differencing it right here to get a difference. We want to look first to see if we need a unit root. So we're just going to take this code right here, and we can pipe straight into it. They're using a data frame and then the vector. I think we only have our series, so we should be good. Let's go ahead and take a look right here. There's the series. Take the series right here. Our series doesn't have close, though. Our series has turnover. And the unit root, well, first off, what does this test tell us? Well, in 201, we talk about p-values, and what's something in 201 they should know about this p-value instantaneously when you see it. If you see that p-value here in 201, you say, ah, that's below 0.05. That is definitely this. We're just gonna keep knocking things out here. So we have the feature, and it's unit something else. Let me get the next one. I'm gonna get the next code going here. There it is. That's it. No, I think it's that. What does that p-value mean to us right here? What does that p-value mean to us? Like the first thing, the KPSS stat is basically a z-score. A z-score is a standardized metric. So is the KPSS stat. That's a standardized metric by which we can derive a p-value. And this is why we don't use things like the David M. Lane applet, because all we need to know about this p-value is what for 100 points. That p-value right there is below 0.05, meaning it is what? That p-value right there is below 0.05, meaning it is what? That p-value is below 0.05, meaning it's what? She's low, right? So what does low mean? When the p-value is low, reject the null. It's statistically significant. Great job, Leo, right there. Stats 1 coming through. It's statistically significant. It's below 0.05. And then you have to ask, well, what does that mean for this data? Well, this test right here is to see if we need differencing. And the null hypothesis could be written on the field looks at the stationary and white noise determined difference needing. Thacker 500 points doing a top tier explanation of what it's doing with the test. So Thacker is 100% right. We're looking to see if it's stationary and white noise and to see if differencing is needed. So the null hypothesis would be that it's stationary white noise and differencing is not needed. So if you think for the classic ways we talk about statistics of we are going to what the null hypothesis here, which you'll hear a lot for test 3 and 201. So the null hypothesis would be that this is stationary. This does not need differencing. That's the null hypothesis. And we are going to what that null hypothesis. Now, you wouldn't talk to somebody if you're doing stats that way. You wouldn't say, like, we're doing business analytics, so we wouldn't say this. I'll tell you what I'd say in business analytics. It's a lot simpler to say. So what would we say? We're going to reject the null, right? So exactly right. Classical terms, we're going to reject the null. But in business analytics sense, we're saying this data is not stationary, or we have good reason to believe this data is not stationary and needs differencing. And the amount of differencing we should do to it is take one, like, first order differencing. So we should do differencing to this. That is the result of this test, is that differencing should be done. We think we have good reason to do differencing, and the differencing should be done to the first degree. Is that making perfect sense right here? That's what that test tells us. The test tells us we have evidence that differencing is needed. So this data, which I can look at that and tell you differencing is needed, because remember the flowy pattern downward means differencing is needed. And the order of the differencing should be first order differencing. So once again, we're going to use the differencing function. Be careful, don't use diff, use the differencing function. Now, if you use mutate, it's going to add a column onto the end of it. And then afterwards, this is a test to see if additional differencing is needed. So we're going to take our series, run the turnover through it. And then afterwards, we're going to take that same value and we'll say diff turnover. And then we're going to see if additional differencing is needed. I do not like how that p-value looks. I wish it would actually report the full p-value. Dylan and others were looking into this. It just reports the p-value at like either 0.01, 0.05, or they're just saying, you don't really need to know that as we get our first disconnect of the day. But now, is this good or bad? Like in terms of differencing this series more, is this good or bad? I've already differenced it one time, as in my series now has an additional differenced column. Please note how the first value is messing. That's what happens when we difference. So differencing was done. And so is this good or bad? Is that p-value you see down here a good or bad p-value? Right there. Is that p-value good or bad now? Is that good or bad? Sorry, Mercer, right there. We're going to do some tool on here in about 5 minutes. Is this p-value right here good or bad in terms of this test? Leo, so it is a high p-value. Now, Leo, 100 points. When it comes to assumptions in statistics, we oftentimes don't want to reject the assumptions. So interestingly enough, this means we no longer need to do differencing. Remember, we're looking for evidence of differencing needed. So now actually we would say there's no evidence that differencing is needed. When we reject the null, there's evidence for the alternative. More on that in test 3 for 201. So we would say there's not evidence of differencing. Remember this graph that we saw just a moment ago right here? So since it's not statistically significant, that means there is not evidence differencing is needed. So we wouldn't difference further. The reason we differenced the first time, and Leo, great job just following along, seeing this new stuff right here. The reason I differenced the first time is because my original data right here, when I ran it, showed evidence of statistical significance that we need to difference. Then I asked, well, what order do we need to difference it? And it said we need to do differencing of 1. That's the code I ran right here where I did the differencing on it to take my original series, and this mutates, it adds a column to the data frame and adds on a differenced series to it. And then I said, well, do I need to do more differencing? And the answer is no, you don't need to do more differencing. If I asked it, well, I don't need to do more differencing, to what degree? It's going to tell me no degree. It's going to say you don't need to do this. So that's what the code is communicating to me here, that You don't need to do any more differencing. You're done with your differencing. So what would be cool to look at now is to go to the auto plot of it. And now what we should see in the auto plot is it should look a little bit more random. Now, I might leave it off right here. There's a problem with this, and Tool 1 should know the name of it. Let me draw on this and see if Tool 1 can give the name, if this was a residual plot, what the problem with this residual plot would be. QQ, straight enough, no outliers. And 475 can talk more about this and how we would handle this. It thickens, right? So now we might need to do a what? For the last question right here, we might return back to this in a little bit here. It gets larger. That's a QQ, straight enough, no outliers, plot doesn't thicken. And this is a violation of plot thickening because we're looking at the leftover unexplained variation. So what could we do for 75 to fix this? What could we do to fix the heteroscedastic nature of this, the uneven plot thickening? What option is there for us related to this to investigate? What option is there, which I'll kind of leave you on that. What option is there? What option is there? You could do a log. I prefer the Box-Cox transformation because the data, the Box-Cox transformation, and decomp is just going to break it into components. Transformations are going to change the way the Y variable works. So you might have data that looks all crazy like, and you see how this is heteroscedastic. Heteroscedastic or plot thickening means that it gets thicker as it goes. Can everyone see the plot thickening here? This is not quite a residual plot, but it does show that there is very small scatter here. It's getting more scattered as time goes, but you can do a transformation via the Box-Cox family of transformations, and we see more of a linear relationship, QQ straight enough, no outliers, plot doesn't thicken, and a more consistent scatter. So the option we probably have for this one, because of the uneven nature of this, is probably do a transformation. So to Kelton's question, last question right here on this, the spikes we're seeing are probably at a lag of what? Which I'd probably go into a seasonal arena on this. The spikes we are seeing are probably at a lag of what? The spikes we are seeing are probably at a lag of what? Like, why are we seeing spikes at a lag of? Probably the distance between this, if I had to guess, is a unit difference of what? A unit difference of what? Which probably we might need some seasonal that. Probably 1 year, which would be 12 units since it's in monthly data. So this is, and so if you're interested in any of this stuff, 201, we like doing this, and it probably looks like magic over here. But who's finding the coding a bit easier, especially with the book? Which I tell you, the fact that he made this book free. Check out this book if you're interested in any of this 201. It's a 100% free book. Dr. Rob Hindman made this book. So huge shout out to him for putting his book online for free. There's the gentleman who made this book. 100% free book going over how to do time series in R. And a lot of the code is pretty easy. The book helps a lot. The book just literally has example of code you can just take. It walks through, shows you how to do everything, and explains it all. So if you want to learn how to do some time series, and he just shows the code in R like scatter plots, and you could just literally take his code. As you can see right here, I'm just going to take this code. Sure, let's take this code instead now. Oh, I might not have the A10 series source. I hate it when he does contingent code. So you could literally just take a code, drop the code into R if you don't have a code in R. You see he's using the A10 series again. He does better with codes in this chapter. Yeah, I tell him that. Don't do contingent codes, Rob Hindman. Don't do that. So that's a good review right there. Did that help people out with some of the questions going into some of the theory on it? 3B, there's 2B. Find the transformation, maybe look for some Box-Cox. Find the optimum value of Box-Cox. Do the Guerrero thing where you pull the lambda. So you want to do a lambda pull right here. Pull lambda on this. Definitely go to the book on it. Helped a few people with this during with some Discord. If you were asking about 3B, you just add the 1 plus the PDQ of it. So you will add the 1 plus the PDQ of this right here. This is what goes into your model. Does that make sense? Try it out. If it doesn't work, message me. But you'll just do 1 plus, and that'll add the constant right there to take a look at it. So make sure to add that in and check it out. But any last questions on 475? We might have time towards the end to swing back to this. But how are people doing on this? What are questions? You just add the 1 plus to get it in there. You're welcome, Thacker, and thank you so much. And that's just what it says when it says add 1 plus. I add it before. You probably do +1 after. I add it before. But that's got it. We're going to head back here. Now we're going to do some tool 1. And great job, Leo and everybody. If you look, some similar concepts about plot thickening. And now we have ways to handle that. Because in tool 1, you might say, well, darn, the plot's thickening. And what would I do? And in 475, we say, well, let's try to transform the data to fix the heteroscedastic nature of it. We have ways to fix things in a lot of classes, and that's where we get into more advanced topics. Heading back here to the main screen. Huge shout out to 475. Great job, Thacker and everybody. How much does 201 topics come into play? My hair is just crazy these days. I'm going to get, I should get a haircut this Friday or something. How much does 201 come into play? A manufacturing company would like to investigate the new supplier of raw material to the product. I think, Zachary, I think that might be for test 3, right? We might put that one on hold. How do we find probability less than or greater than or equal to a certain value? So are you talking about because that would be David M. Lane, which luckily is not directly on the test. So we have here manufacturer and probability greater than or less than. So we wouldn't do that. We can do a sampling distribution. That would question peel up next. And so we wouldn't do a sampling distribution question where we had you find probabilities on this. It was Canvas content number 7. Oh, let me go take a look at that. That'd probably be good right there. New supplier of raw material. Okay, let me go find that because that's probably going to hit both bases for us. Let me go grab that Canvas content question and we'll do that next. So 201, we're back doing 201 here. And thank you, 475. I always try to do as much between different classes as I can. So 320 could hop in and we'll probably try to do a lot of 201 focus since it's test day. Oh, wrong button. I'm trying to get that Canvas content question up so I can look at it. And I can do it. Canvas content number 7. Here we go. 1 second. I'm going to find this one right here. A manufacturer. Here we go. Here it is. Okay. Okay. Let's go check it out. Doubt that on something because we use the applet. Yeah, exactly. Good answers right there. Correct. And so let's look at how the exam might look. Let's hop into it. Here we go. So once again, we will not be finding probabilities because we won't be using the applet on the exam. But what we will do is we will answer questions like this about conditions, or we will answer questions on things like what is the mean of the sampling distribution, what is the standard deviation of the sampling distribution. All those are possible questions. Now, whenever you see a question, the number one thing to do is do what? Whenever you see a question, the number one thing to do is do what? Whenever you see a question, the number one thing to do is to do what? The number one thing, notation, brother. You know what? Leo, you have earned a MuBot quote with that. I love it. Quote 196, notation, brother. So Leo right there. Quote 196 for Leo right there. In class, are we reviewing? We are reviewing. We want to first write our notation. We could check conditions and stuff, which this question walks us into. But yes, great job, Leo. I love it. And so I'm going to grab, I have a picture of this right here. Let me go ahead and drop this in here. I need to bring back the rest of this graphic. And let's talk about what we have right here. Okay. So now we are going to talk about the notation first. Notation first. Now, we're not going to look at the question yet because we're going to learn more from this than just what the question asks. What is any of the notation in this question? Be careful, I might be highlighting more than what you need. What is any of the notation? What is any of the notation? Any of the notation in this question. And then I'll narrow down our field of eyes. You're looking at your formula sheet, and here's what you see. What is any of the notation? Leo right there has already said, careful, Leo, careful. This is tricky, 100 points. This is tricky. N is going to be 500, and that's N. That which we rarely to never use, and that doesn't stand for, no, Leo, 100 points, you got this. Very common error. Little n is sample size. Capital N, which can also mean normally distributed at times, is also used for population. This won't be used in equations. That it's extra information which we could use for another condition check, which we'll do here in a moment. That'll be used in a moment, but not for this question right now. So we're only missing one bit of notation right now for this question. What is the only bit of notation? Well, two things technically. Two things could be derived right now, or one is given, the other could be derived from it. The only other things we're missing right now on here would be what? And capital N is population. That's the population they're taking from. So what is the other thing we are missing on here? P and Q, great job, Robbie, right there. Excellent work, Robbie, 100 points. So, and Seth put right there, not P hat, and careful with the decimals, not P hat, and careful with the decimals. Good work. P. And look how it's written. It doesn't say this is from the sample. It says if the defect rate is this. So it's trying to tell you this is the truth. The way it's worded, it's not that in a sample, and as Leo's pointing out there, P hat would be from a sample or what we see in a sample. So in good work, Seth, don't worry, there's a lot, like, very common question, what's the difference between P and P hat? P hat comes from a sample. So this question could say something like, they find 50 defective. Okay, so I've just added to this question, they find 50 defective. What additional notation have I added to this question? It just has an additional, they find 50 defective. So what have I added to this question now? The question has an additional, it says they find 50 defective. So it says they find 50 defective. What additional notation have I added? It says they find 50 defective. They're seeing if certain things are defective. From the 500, they find 50 defective. Just has more info on the problem now. What is that in notation? So we just have to always know our notation. We haven't even gotten to this yet. So what? Close, Leo. I think you're on. I think you can. I think I know how you're getting that. Arden is right. Be very specific. The 50 is not quite P hat though. I think I know where you're going with that. I think I know where you're going. Maybe 20%. Malia, good question. Maybe 20%. Similar to Canvas content. So 50 is not P hat though. What is 50 in notation? What is 50 in notation? 50 is not P hat though. You can solve for P hat now. It's X. And so since we know X, how do we get P hat? Solve for P hat now. We're just, once again, we can solve this question here in a moment, but understanding all the notation is key. Hey, Priya, great to see you here. What is P hat? So P hat is X over N. And so solve for that. Solve for it while I'm solving for it too. What is P hat? Great job, Zachary and Seth. Great work. And then say this to yourself. In their sample, 10% were defective. In their sample of 500, 10% were defective. Does that make sense logically? Because that's the sample proportion. In their sample of 500, 10% were defective, which is 50 out of 500. So if it makes logical sense when you say it, because that's what P hat is, great job, Marissa, right there, 100 points. Just try to make sure you know that P hat is the sample proportion, because it's how many successes were there out of the sample total. And right now, things are equally likely. So if things are equally likely, you can just do X over N. It's just any part has the same probability. So P hat has, you can do it as a percent or as a decimal. Arden, good question right there. Multiple choice right there, Maxim. So this could be reported, the proportion that are defective in the sample was 0.10, or the percent that are defective is 10%. If there's a decimal issue with your grading, let me know. Look over your questions to see if it gave you wrong points because of a decimal issue, and I can correct it. So now that we have all this information, which of these does it look like we're using? Line number 1 or line number 2? Which of these are we doing? We're asking, is a part defective? That's the question we're asking. Are we working with sampling distribution 1 or sampling distribution 2? We're working with sampling distribution number 1 because we're asking, is a part defective? And that is a what question. To say, is a part defective is a what variable type? Is a part defective is a what variable type? Great job, Zachary and Amber and Matthew and Kevin. It's categorical, right? It's either defective or not defective. And once again, the success failure condition, which Seth is pointing out right here, which will be the third condition, doesn't have to deal with it being binary data. It has to deal with there being at least 10 successes, at least 10 failures. Although this is binary data, the success failure condition is, are there at least 10 successes, at least 10 failures? Now that we have all the notation, to check the success failure condition, we go in here and we do the following mathematics. Success failure condition is NP greater than or equal to 10, and we'll never make it exactly 10. I'd find any question that was exactly 10. NQ greater than or equal to 10. So solve this now. Don't use the... I'm trying to think. Maybe send it to me, Colton. You might be mixing methodologies. You should be able to try doing a transformation with the mutate. You should be able to do that. Try doing a transform with the mutate. Good questions, Colton. Try to mutate, transform it, and append a column to the data frame. That should do it, I would think, theoretically. So solve for these values right here. How did you find X? The problem, pretty good question. This problem didn't have it. I appended it. So I added it to this problem. I said they find 50 defective. I added that extra sentence. The problem didn't give it. Zachary has the right answer right here. Zachary has taken N, which is 500, times it by P, which is 0.03. I'm going to disappear her for a moment, and found the following of 15. And once you find NP, NQ must add up to 100. So that would be NQ right here, and solve on your calculator and double check. A good way to know, should passed. You shall not pass. Well, you do pass right here. So both of those are greater than or equal to 10, and they must add up in totality to N right there. How about, is the 10% condition passed? So the answer is yes, the condition is passed. How about, is the 10% condition passed, and how do we check that? So let's put a new question right here. And so is the 10% condition passed? So take a moment, answer in the chat, talk about it. Is the 10% condition passed? So how do we know this? And great job, Priya, right there. Take a look at what Priya's doing, 100 points, Priya. To do the 10% condition, we ask, did we sample less than 10% of the population? That's the 10% condition. Did we sample less than 10% of the population? Maria, you are correct. And so the reason is, and people are putting in the chat, we ask, is our sample size, N, less than 10% of the total population? This one actually gives it, hence some people sometimes say, well, how would I solve this? And people are showing mathematically in the chat right now, 500 divided by 7,000 is equal to, is it that? Something close to that. There it is. There we go. Exactly. And Priya's pointing out it's 7.14%. Oh my gosh. Brian made a decimal error. That could easily happen right there, which is 7.14%. Be very careful. We are all capable of decimal errors. So it's 7.14%, or as a proportion, 0.0714. So we do pass it. As long as these are randomly selected, less than 10% of the population, and success failure. What does that mean? To pass all the conditions means that the distribution can be whatly described. To pass all the conditions means that the distribution can be whatly described. Described as a what? To pass all the conditions. It'll tell you, and tell me if you think there's a problem with the way it calculated. If you're like, I don't think this did correctly, just let me know and we'll fix it. I'll look it over. So normal, exactly, the normal curve. Do you need to check conditions to calculate p hat? Yes or no? Chat, just spam the answer. Do you need to check conditions to calculate this p hat right here? P hat, which is x over n. See, even I got to practice. No, you don't. Do you need conditions to calculate the sample mean? Do you need conditions to calculate the sample mean? Where's our cheat sheet for this one? Here it is. Do you need conditions to calculate sample mean? No. No conditions for the sample mean. The sample mean is just the sample mean. It's what did we get in a sample. All the conditions, the reason to check conditions, the reasons to pass conditions are to see for either of these distributions if we can use the what curve. You just find it. You can always calculate the mean, just amount of observations or sum of observations over the sample size. Checking conditions is to see if we can use the normal curve. So once again, the conditions are random, 10%, and then we what? The conditions are random, 10%, and then we what? That actual minus predicted, wrap, Matthew, wrap. We pause. So at Matthew, it's residual rep, actual minus predicted. So we pause. And why do we pause? Okay, jump right there. We pause because we check if it's categorical or quantitative. If it is quantitative, the third condition is what? If it is quantitative, the third condition is what? It's on screen. If it is quantitative, the third condition is what? It is large enough n. We'll head over here to lecture. So I'm not blocking it on the bottom. If I have different slide views for different classes. If it is quantitative, the third condition is large enough n, which states, and there are, this is all right. I always kind of add to the slides, as you notice. Large enough n states, no worries, Kaya, that the more what a distribution is, the larger n needs to be. The more what a distribution is, the more what a distribution is, the more what a distribution is, the more skewed. And then you notice the more skewed it is, the what or any, think about why it's called large enough n. The more skewed it is, then quantitative. Leo, I need to start doing that. Quantitative large enough n. Yeah, Leo, that's pretty good right there. Leo, points, add viewers. 500. Leo, that's a great way. Hertz linear diffuses then it's an iffy. Comment on that. That's an iffy right there. That's an iffy. I'm like, definitely comment on it. Sometimes you fix one thing and damage another. So yeah, quantitative for large enough n. Great ways to memorize stuff right there. Quantitative large enough n. Categorical doesn't have it. It's success failures for categorical. The more skewed, the larger n needs to be to make it normal. And we see that here visually speaking. This distribution is very skewed. You would say to me, n needs to be probably what? Like that's the original data. Since the original data is very skewed, you would say to me, well, n probably needs to be at least this. Zachary, 100 points. Very correct right there, Zachary. Needs to be at least 100. And it's basically normal then. Basically normal. It'll get even more normal, just more and more normal. And so probably 100, we're not, but here's the thing to know. Is 50 going to work for all data? Would a sample size of 50 work for every single data distribution? Like for all data, does 50 work? So does a sample size of 50 work? No. Sample size of 10, sample size of 100. 100 works for pretty much everything. What if it's ridiculously super duper skewed? Maybe 200. But the more skewed it is, the big thing to know about large enough n, the more skewed it is, the larger n needs to be. So if it's normal, you can do 1. If it's pretty normal, 5. If it's skewed, 30. If it's very skewed, 100. And you might say, well, how would I look at it? We usually use words on the test to make it very clear that you understand the concept that the more skewed the original data is, and what are we saying original data? If I ask people, how many push-ups can you do? Maybe the distribution. Right here. I say to people, how many push-ups can you do? And the distribution of push-ups looks something like this. The distribution of push-ups looks pretty what? And we can draw our own, actually. Oh, I hit the button there. The distribution of push-ups looks something like this. So tell me about the distribution of push-ups right here. Cool, do that. Ooh. Little secondary peak right here. It's very skewed. It's bimodal, but it's got some skew to it. Does that make sense? A lot of people doing 0. That's all right. Some people, the average amount of push-ups is 13.7, but it's right skewed. The central limit theorem is going to be used right here, which is a fundamental theorem of statistics. The central limit theorem, teaching the test moments. It's bimodal with right skew because towards the high side. So what if I go and talk to 2 students and say, how many push-ups can you do? And I say, I'm Brian Stevens. Say, oh yeah, you're that guy. That is the what of 2 students right here. That blue dot, here's my 2 students I talked to. This person said 18, that person said 16. This is the what of those 2 students, which is 17, let's say. That's the student who said 18, that's the student who said 16, this is 17. That is the what of the 2 students. That is the what. That is the mean of those 2 students. Now I'll go talk to another 2 here again. That person, wow, 30 push-ups.
Wow.
And this person did 15, so that's the mean of those 2. And then, sorry, that's right. Wow, very dichotomous right there. And there's the mean of those. And so you can see we're just doing, and if we repeat this process repeatedly, it'll start to build a what for the means we might see. If we keep doing this, does simple theorem just tell us about the shape of the curve? It tells us the shape will become more what? Oops. It tells us the shape of this curve will start to become more what, which it hasn't yet. It'll tell us, and we're getting the distribution, which is the shape of this curve will start to become more what? Wow. Central limit theorem, you're absolutely amazing. The shape of this curve will start to become more normal, and the curve will also get water. The curve became, if you look at it as I increase n right here, the curve becomes more normal. Here's it a little bit normal. Here's it normal, a little bit of right skew. And here's a larger n, and this is just how many times I do the simulation. And it's getting tighter. And that's the two things of the central limit theorem. The central limit theorem states, which is a fundamental theorem of statistics, the central limit theorem states that the distribution of the mean, not the original data, not the sample data, will become more normal and tighter by a factor of square root of n, i.e. larger n, more normal, larger than n condition, and larger n, we are dividing the original standard deviation by the square root of n. Can anyone take a moment right here and tell me what the now be careful, I'm going to ask a tough question right here, ready? Can anyone tell me what the standard deviation for the distribution of the sample mean will... Seth, are you answering my question already? I'll do a more difficult one in a second, Seth. Damn you, Seth. Seth, how'd you get that? Seth answered my question, what the standard deviation for the distribution of the sample mean would be. I've asked it too many times in class. Seth, how did you find that? How did you know that theoretically? And you have to see this number to know it. Seth, show the mathematics right here that you're doing. Yeah, I agree. We got to throw another 500 on top. That was a big wow moment right there. Seth, another 500. That is a big wow moment. Zach, I agree with Zach right there. I concur. How did you find that, Seth? So Seth took oh no, we're not doing kurtosis. Okay. I'm not even gonna find kurtosis of this curve. What's the normal curve says no kurtosis. So what Seth did is Seth took the original standard deviation of 5, and then you divide that by the what? You take the original standard deviation of 5, and you divide that by what? The equation, I'm going to take a screenshot here so I can write on it. The equation to find this is, great job, Leo right there, excellent work, Leo, is you take sigma, and down here, this is sigma over square root of n. The sampling distribution has a smaller standard deviation, but what is the mean for the bottom distribution? Like this is the mean right here. And what is the mean for the bottom distribution? The mean for the bottom distribution is the what? Like that's the mean. So the mean for the bottom distribution is the what? And this is the sampling distribution of the sample mean. It's just going to be 16 because the mean is the mean. Now in notation, this is mu y bar, and the other one is sdy bar. But the formulas for it are over there. Mu y bar is mu. And it's just, that's the sample size right there, Leo, no worries. Mu y bar is mu. The original distribution has a mean of 16, so the lower distribution has a mean of 16 also, because the mean of the original distribution is the mean of the sampling distribution. The original standard deviation gets smaller by a factor of square root of n, and that's the standard deviation. So these are the concepts on your formula sheet where it says the mean and the standard deviation. So the mean for the distribution of the sample mean is the mean. Like, just follow along right here. What will the mean be of the lower distribution right now? What will the mean be of the lower distribution when I run the simulation right here? So Rock knows. It doesn't matter. What will the mean be of the lower distribution? What will the mean be? 14.89. It's just the mean of the original distribution. But before I hit the button right here, because we already know the answer to the first one, the mean doesn't change. The mean is just going to stay the mean. What will the new standard deviation be? Remember, the central limit theorem states, it's a fundamental theorem of statistics. The central limit theorem states that the new standard deviation will be tighter by a factor of square root of n. So take the original standard deviation divided by the square root of n, which is right here. So the new standard deviation will be what? I've got a guess in my head of what it'll be. 5.315. The Priya's got it right there. And all they're doing right there is they're dividing. And you notice how it rounded up. The simulation doing such a great job right there. And great job, Robbie, showing the mathematics also. Just probably one of the most common errors we see is people don't divide by the square root of n, because that's the standard deviation for the distribution of the sample mean. The original standard deviation is 7.68. The standard deviation for the distribution of the sample mean is going to be tighter by a factor of square root of n. So as n gets larger, the standard deviation gets smaller. Central limit theorem. Good stuff. Let's do another topic right here. Are people feeling a little bit better about these concepts? We did both sampling distributions right now, which I know is the newest material, and it's one of those trickier topics, but we'll hop back to the main screen and do another topic. And great work, everybody. Good practice. Yes, yes, yes. We like that. And once again, remember, I gave a pep talk today in class. Keep doing the homeworks and quizzes. Even if I had a student who is like, what is the interpretation of R-squared for the decision tree? Ah, good look at that. Look at a little R-squared interpretation. Yeah, people are asking about decision trees. Let's do decision trees. I'm going to bump that up on the list. We haven't done decision trees lately, so that's a good. And then we'll have Leo's question here in a moment. We did the manufacturer by incorporating that in here. So we'll do decision trees next. Then Leo, your question coming up next. Question 7. We might not have enough time, but we might be able to do it during class. I'm going to put it on the list. We'll try to do as much as we can. Matthews, thank you so much. And we got Leo, your question right after Priya's. So let's do a little decision trees here because we haven't done decision trees in a while. So good stuff. Decision trees coming up. Let me close this data set. Whew, we're all going to get a good sleep. Get some relaxing with spring recess. Oh my gosh. One sip of coffee. Last sip. Coffee done. Get that coffee. I think there's another question right here. 2 seconds. Let me put the timestamp. Plot of 7:38. Heading over here, back to the main screen. Great job, Leo. I saw Leo is just doing an awesome job today, putting all those great answers. Blank percent of the variation of y variable can describe by the variables in the tree. That is correct, Leo. So let's take a look at a decision tree right here. When it comes to decision trees can take what kind of y's or what kind of x's. No, you don't have to state the x variables in the interpretation. A decision tree can take what kind of y's or what kind of x's. A decision tree can take what kind of y's or what kind of x's. A decision tree can take what kind of y's or what kind of x's. Great job right there, Leo. It can take, it takes one y. That is correct. Decision tree takes one y. And the variables we wouldn't use would be the identifiers or categoricals with too many levels. And it can take a categorical or quantitative y, categorical or quantitative x's. Let's see why people go to church. Take me to church. Dun, 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 dun. So I'm eliminating the variables. I can't sing. I'm eliminating the variables right here. You're like, Brian, that was cringe. And I say, I know. That's me all day long. I'm eliminating, I think that's the only one. I might have eliminated the other ones already. I might have. I don't know if I see any ones. I can't tell. We'll find out the hard way if I put in. So categoricals, lots of x's and one y. The y does not need to be quantitative. Good answers right there. The y can be categorical or quantitative.
It doesn't matter.
So the y can be quantitative or categorical. The x's can be quantitative or categorical. A categorical tree will predict the probability of someone being in a certain group. Quantitatives will predict the mean for that group. So let's see why people go to church. Now, the first most important split right here is the first split. So here's the first split in the tree. Boom. The number one reason people go to church is why. Now, once again, this doesn't mean you go to church if this is true about you. It doesn't mean you don't go to church if this is true about you. But you might be saying, well, that kind of makes sense. What is the number one most important guiding our path here on why people go to church? This is real data, so we get to see some real insights here. Some ground-shaking research. So what does it say right here? Oh no, what did it tell me if SI said something? I might need to talk to Alyssa. If she said something like it only does categorical or quantitative. No. Decision trees do quantitative or categorical. Please tell me if and I can say things wrong too, so you gotta watch out because I've said things that are incorrect before. No worries. Good job. Political beliefs. Are you conservative or are you a mix? Are you mixed or liberal? So, we asked, what's your political belief? Someone said, I'm conservative. So they'd go over here. So every time you see a blue dot, that represents people who are conservative who go to church in this group. These red dots are people who are conservative who don't go to church. Once again, please don't assume anything about anybody. If someone says, I'm conservative, that doesn't mean they go to church. If someone says, I'm a mix of beliefs, like they're kind of not quite liberal, not quite conservative, they're a mix. Well, these would be people who identify in those groups, mixed or liberal. And we do have the people who do go to church, and we do have the people who do not go to church down here. Just kind of making sense. And there's a little bit of a difference. There's some difference, but once again, don't assume anything. This is for this data only. And once again, people are people. The next split we have right here is how much do you drink? So who's really going to church right here? Can you describe for me the person to most likely go to church? The person to most likely go to church is who? And please drink responsibly. Gotta say all the adult stuff here. So, but no, I don't say it as a joke. Please drink responsibly. Get an Uber or a Lyft if you're out. So Leo, you are correct, but follow the tree down. Whenever you're doing this, follow the tree down right here. Follow the tree down. So follow the tree down to the very bottom. So you'd go here, then here. So tell me in totality about the person most likely to go to church. Tell me in totality. Someone who is conservative, who drinks less than 4 drinks a week. And look how we go down right here. Now, how could I, this is a good note to take. How could I look at these groups and examine the groups to see the proportions or the means of these groups? Proportions if it's categorical or means if it's quantitative. How could I further investigate and look at the groups that I've created? The leaf report, Leo, exactly. The leaf report, because these are the leaves of a tree. Think of a tree just flowering away right there. Trees flower, right? We'll go here to the leaf report. And the leaf report is telling us the terminal leaves of the tree. When I say terminal, I mean there's nothing after them. Look at these 151 people. They're right here. There's 125 of them that do go to church and 26 that don't. And there's the description of these individuals. That's why we're doing some review here, Maria. Good questions. How do you tell which split to go down? Just think of it as a pathway. Like, if you think about this, we'll have to take a screenshot here. So people who go to church are what color on this graphic? People who go to church are what color on this graphic? People who go to church are what color here? You might have to go back and look at, give a little hint right here. If you're wondering how we knew this, go to the original data and you'll see the S's up here. They're blue. So that's the reason we know this. Oh, thank you, Leo, right there saying speed run help. Yep. And I try to do topics really quickly in the speed run. So the blue are people who go to church. The yes is up here. And you can see group 1 is the most likely to go to church. You could see leaf report. You could see split history. More on split history in a moment. So when you think about this person says, I want to be the most likely person who goes to church. And they say, am I going to go left or right here at this split in the road? They say, should I go left or right at this split in the road? Which way are they going to go? I want to be someone who is most likely to go to church. Nice job right there, Maria. So which way are they going to go right here? They're going to say, I want to be a most likely person to go to church. They're going to say, I got to go over here. And then they say, okay, I'm at another split in the road right here. And then they say, I want to be a most likely person to go to church. So now which way do they go right here? So they said, I'm a most likely person to go to church. See how there's more blue over here? They're hanging out the blue right here. So now they're going to go right here, and then they're also going to go to the left. You see how this is like a pathway? They got this road decision right here. No worries, Priya, you got this. And then they go here and they say, which way do I go here? They say, I go left. Which way do you go, George? That's an old meme. I think it's a cartoon or something. So does that make sense? They've ended up down here in what we would call leaf number what in the report. Does that make sense? The Y variable is shown by the proportion of people right here. I would call this leaf number what? This person has ended up in leaf number... so when you do the terminal leaves, the leaves at the bottom go in order by the way they're written, by left to right. And that's the ordering of the leaves, leaf number 1. The blue represents people who go to church, and that is found by looking back here and seeing the blue is the yes. Does that make sense? So blue is people who answered yes to the question, and that can be found right here. That's associated with these proportions right there. So since we know they're in leaf 1, we can look at leaf 1. Now, this person would have an 82.58% probability of going to church. You're welcome, Zach. A lot of speedrun review right here today. But let me ask you a more difficult question. What percent of conservatives, what percent of people who are conservative go to church? Now, this is a question that gets a lot of people because the answer can't be derived directly from what's on the screen. So the question is, what percent of conservatives go to church? What percent of conservatives go to church? Now, when you think about this, let's kind of break it down what we have. Well, you can get a good guess of it because what we're looking for is we are looking for this. So the visual right there can give you a guess of it. That might be right, Zachary. That looks right-ish. Maybe. We'll find out. Good. Zachary, if you want to show the mathematics, write down the mathematics, and that might be right. What we're looking for is the sum of which two leaves. We're looking for, and great job, Pri and Zachary, we're looking for the sum of which two leaves. Which two leaves are we looking? Because we're trying to find out this specifically. So which leaves are we investigating? 1 and 2. Does that make sense? Because these people split apart. Like those people are just being split. Like if you add up these people, they'll add back up into that. Does that make sense? So they would add back up into that. So we're actually looking at this down here. Here, we'll highlight this way. How many of these people go to church? Just tell me how many of these people go to church right now. Ooh, you could do it pretty quickly with the output this way. How many of these people go to church? And great job people showing the mathematics in the chat. How many of these people go to church? There's 186 who go to church because that's the answer to the why question. Does that make sense? Does everyone see how there's 186 who go to church? Does that make sense? 186 out of that right there. So that's the total. So it'd be 186, which is the sum of those two numbers. And you could actually just take the total from it right there, which that value is also the sum of all these values. Does that make more sense? Sophia Caesar right there. We're doing a lot of questions, and I cover a lot of these types of examples in the speed runs. That's a tougher question right there. So we're trying to do as many as we can. So good questions. Review it. Hopefully see it right there. Let's do one more thing with this output, and then we're going to interpret the R-squared too. Well, the R-squared is the percent of variation in Y, and in this instance, explained by the tree. The way the conversation goes on R-squared is either blank percent of the variation in Y is explained by X, and that's the interpretation we use where. So when we do R-squared interpretations, we either say blank percent of the variation in Y is explained by the variation in X, or blank percent of the variation in Y is explained by the variables in the tree. Now, do remember, we need to put interpretation right here. And we will give context. You will not get full points if you do not give the context. Variables in the tree can remain variables in the tree. And so I think right there, Leo's done it. 10.9% of the variation in whether someone goes to church is explained by the variables in the tree. Done. That's on the test. 100 points right there, Leo. 4 points out of 4. But be careful. That is for what chapter? So this one right here, Leo's done it properly. This is for decision trees. Yep, that is how you spell it. I don't know how to spell anything. That is for decision trees, where the first interpretation is for what? Where we say blank percent of the variation in Y is explained by the variation in X. This first interpretation is not for decision trees because we're talking about a singular Y and X relationship. Cassandra, let me know, and I'll be checking emails. I've been teaching everything. Cassandra, let me know. We can try to fix things. Click the Proctorio support. Try a different computer. Try a different browser. Regression. I'll be looking into that. I've been replying to as many emails as I can. Yay! We'll get things fixed up. Keep me informed of issues, and then we can work around it. We can find a solution. Try restarting computer. Try restarting browser. Click. There should be a Proctorio support button in the corner of your browser, and try reinstalling the Proctorio app. I did, but my time is still counting down. Is it currently up, Cassandra? 2 seconds. Is it currently up? I'm going to fix it here live. Do you currently have the exam up? I'm going to add more. Thank you, Cassandra, for telling me this. Fixing problems live. You would think it's so funny, like, man, Proctorio. I like Proctorio and I hate Proctorio. That's all I'll say about that. Because let me just tell you this: probably you're doing nothing wrong. Like, I don't think, like, no, is it still open right now, Cassandra? I'm going over here to my screens to looking up stuff. Okay, I see it. How much time have you lost, Cassandra? How much time have you lost on your exam right now? How much time do you feel you have lost? We're probably, it looks like we're opening my Pearson back up. Looks like my Pearson's had a problem today. Yeah, make sure to do Chrome. Don't use Safari, use Chrome. How much time have you lost, Cassandra? And then I'll add it back on right here. 10 minutes. I'm going to give you 15 extra. Thank you, Cassandra. So I'm adding extra 15. Thank you so much for informing of this. I tell everyone, reach out to me as quickly as possible. I need to check emails too. Here we go, Cassandra. I've added on the extra time. Let me know if there's any issues. Cassandra, 500 points. Thank you so much for reaching out. Keep reaching out. We're here to give everyone fair exams. That's our whole goal. Please reach out. We might be able to, Connor. We'll try. Good luck, Cassandra, there. And thank you for reaching out. We're going to do our best to make the exam as fair and as even as possible to everybody. And so we want to put that extra time on there to make sure you're treated fairly for your exam. Let me know if there's more issues. Feel free to hop in the stream, and we appreciate that. We're here to do that. But good stuff. Head back here to the... Oh, we got one more thing to talk about. Nope. So the last thing right here, the last thing over here, is if we're talking about r squared, how can we view r squared? If we're talking about r squared, how could we view r squared? If we're talking about r squared, how could we view r squared? If we were talking about r squared, thank you everyone for all that positivity. How could we view it? I just one question about 3B. Yeah, message me on Discord, Connor, and I'll definitely reply to it. Is it due today? I think it's due today. Exam day and test day. Well, we talk about it as a percentage, like 10.9% of the variation in whether someone goes to church is explained by the variables in the tree. But also, how can we view the r squared after each split? Like the history of r squared after each split. What could we do to view r squared history, like the exactly free right there, the split history? The split history right here is going to show us the increase of r squared after each split, and that's what the split history shows. So good term to know right there. The split history shows the history of r squared after each split. Not quite P and Q. Good answer, Seth, right there. P and Q won't apply to this. Oh, no worries. You got this. Good practice. Exactly. When it flattens, we generally stop splitting, which we might have some flattening going on right here. I'll probably readjust it here in a moment. But we might have where it's kind of leveling off. We got a big jump at the start. So the initial jump from 0, I wish it plotted that. Maybe it's doing something. Yeah, political belief liberal is the next split. How much people talk to people on the phone. So the people least likely to go to church. Ooh, interestingly enough, it's people who have a mix of belief who smoke are the least likely to go to church. The most likely to go to church are the people who don't drink and are conservative. I'm going to split it there. And have not done illegal drugs. So it's very interesting looking at that. Also, each split increases r squared. Oh, no, it doesn't decrease correlation. R squared and correlation are kind of one in this. They're not the same. But r squared and correlation have the same sort of relationship with this. Also, we wouldn't really talk about correlation with the tree because it's like categorical and quantitative variables mixing up. 7 and it splits, right, Maria? This would be too much for the. This is too much for the test. We're not going to do a tree that big on the test. But each split will increase r squared, so r squared must go up after each split. So if you split the tree, r squared will go up. Does that make sense? Every time I split the tree, r squared goes up. So the question of how much do I split the tree would be decided by the split history, which is the history of r squared. Oh, and it's going to explain variation. So what it's going to do is it's going to decrease the unexplained variation. Is there time to go over residuals? I think so. We're going to do Leo's question next. Let's do a little residuals. I think that's good because we haven't done that. So we just did decision trees. I'm going to put your question after Leo's. Test 2, residuals. Do you have a question that goes over it? Let's go back to main screen. R squared represents percent of variation explained. Make sure to have those definition down. Blank percent of the variation in Y is explained by the variation in X. Blank percent of the variation in Y is explained by the variables in the tree. Good stuff. 3 splits is generally good. We look at where the R squared levels off. Good questions, everybody. Great question. Let's see. We got Leo's question. Thank you so much, Leo. The question is, you said question 6 part 2 on the... And if you're looking, there are... Ooh, I like it. So let's take the question right here. We haven't talked about this stuff in a while. We have not talked about this in a while. So let's see. Question 6. Good question, Leo. And let's drop it in here to a Word document. Okay. Careful. Careful. Here we go to the main screen. Let's check it out. Okay, this is practice exam, question 6. So do realize, I do want to point this out, and do not worry. But if you want a full review of these questions, I think I have a full review of every one of these over here on the practice review test. So question 6 around here, that's sampling distribution. Is it this one? We change the numbers sometimes on the question. I hate that. That's an at least one question. We're sampling. Randomness and simulations. Oh, is it not on here? No. But you could also go to the key. There's the key up here too. Do I not have a review of this one? Yep. Less than 0.5 means statistical significance. That's correct. So check out the review videos. All this good stuff. Are you talking about this question, Leo? I think it's not. It's statistically significant, unlikely due to random chance. To Priya's question. So I'm going to type Priya right here, and then we're going to do this one. Statistically significant. It is unlikely due to random chance. So if it says due to random chance, the answer would be no. It's unlikely due to random chance. A major airline wants to find out if additional charges for baggage affect the airline passengers who choose to fly and how often they fly. They decide to survey passengers who fly on their airline. The airline decides to randomly select 30 flights over a 1-week period and survey all passengers on those flights. Be very careful. Don't put the answer in the chat. Take a vote on which one of these it is. So take a vote. I've got the vote going here. Take a vote on which one it is. Send me a message. Thank you, Connor. So I'm going to tell you the answer here in a moment and why we know it's the answer. I'm going to tell you the answer and why we know it's the answer. So we're just giving this a moment.
It doesn't matter.
Oh, no, Rock, wrong. How did people know that and why? We had... Oh, no! It was someone answered differently. We had 100% for a moment. Why is it? Well, Leo, you are correct in your answer. Zachary, more points right there. Those 1,000 especially go out Zachary right there, pointing out keyword is all passengers, meaning they have done a what to these flights? They're serving all passengers on these flights, meaning the flights are the clusters, because when you do a cluster sample, the clusters will have a what done on the clusters. Because this is just, they're taking all people from these flights, a census on the clusters. Does that make sense? And we're at 73% getting it right. We had 100, and I was like, yay! And then it dropped, and I was like, no! So when you see cluster versus stratified, how could they do flights where they acknowledge, describe census? That means they take data on everybody on the flights. A census means we have data on everybody on the flight. Does that make sense? So when it says they take data on all passengers, the all passengers part is a census on the cluster. So the flight is the cluster. It's the group you're taking. And then the census is talking to all passengers. In what ways could we stratify flights? Think about if you've ever went to an airport, what way do they stratify their flights or passengers? What ways are passengers stratified when they go on trips on a plane? Different flights would be strata, correct. By company, class. Ooh, I like class a lot. Like first class, second class, third class, all that stuff. That's great right there. Boarding group, that's a stratification. I'm thinking like, what about globally? Like there's 2 types of flights generally if you go to an airport. You go into the airport and they say, are you traveling what or what? And that's a stratification right there. So we'd acknowledge a difference. We'd say, are you traveling this or this? So usually you walk in. Katie, pretty much. And right here, if you notice this, would it be a good sampling method? And so, Katie, great questions right there. If we take all domestic customers to understand our customers, is this good sampling? So we work for Delta, and we're going to take all domestic customers to understand our population. Is this good sampling? This would actually be clustering because we're taking all domestic customers. No. Leo, they'd be undercover bias, right? Under coverage. So what they'd actually do is we would take a certain percentage of domestic and a certain percentage of international. Does that make sense? You would take a certain percentage of domestic and a certain percentage of international. So when I talk about this right here, this is stratifying because domestic and international are whatting between the groups. Think of our keywords. We're not doing a census of those groups anymore. We are starting by doing a what between the two groups. If you decided there was a difference between the two. Yep. Correct. We're talking about there's differences and we're acknowledging a difference to start, and then we're sampling within these groups randomly. Does that make sense? We are identifying a difference here to start, and that's where you have strata. We are, as Zachary said right there from the notes that we've written, we're acknowledging a difference. So these are strata now because we're acknowledging a difference between the two groups, and we're saying we have domestic flights, we have international flights, and we're going to take a percentage of each. Where in the top with cluster sampling is done when you have right here clusters of what is thought to be randomly put together groups, and then you do a what on the clusters. You must see this for the cluster sampling to be happening. You must do a what. Yeah, Zachary, we could. We might have enough time. We'll try to go as much as we can. Zach, thank you so much. I think that helped a lot. There's always there's a click moment. Sometimes they're like, oh, okay. If he takes all of that, that's a cluster. Or if he acknowledges difference as stratifying. Great job, Zach, right there. So when you see cluster, you will do a census on the clusters. If you see strata, you will be acknowledging a difference between the groups. Both of these deal with groups, but in clusters, I think it is. But I'll tell you this much: I am not joking. If we said, let me do this. You ready? Let me do this. You ready? Put in the chat as I write these for a moment what these are. Okay. Leo gets my tricks. The first one right here is we collect data on freshmen, sophomore, juniors, and seniors, and that's stratified because you're probably going to select a certain percentage of freshmen, sophomores, juniors, and seniors, not going to go and collect all. Great job, Seth. And then the next one is in-state versus out-of-state students. That's another difference being acknowledged. That's stratifying again. Now we're talking about people born in Tennessee and not born in Tennessee. Here we'll do the color shirt that I've marked. So these are all differences between groups. Born in TN, not born in TN, have kids versus don't. And now the floors, and then on everyone. There you go. Why did I mark on everyone? Because of everyone on those floors that we select. So when we said we're taking data on everyone on that floor, the floor is the cluster, and then the everyone on that floor is the census of the cluster. So seeing these things, how could you mutate an STL model? You're going to probably have to message me that, Colton. Well, don't mutate the STL model. Mutates are for data frames. Mutate the data frame. Then you want to data frame, mutate, like we're piping here. Data frame, pipe, mutate, pipe, STL decomp. Good question, Colton. You make my brain think right there. So the floors are the clusters, and then everyone on the floor is the census of the cluster. So these key terms right here. What is the sampling frame? All passengers that fly on any airline. Ooh. When you hear sampling frame, what do you think? If you hear sampling frame, you think of what? Oh no, he's asking about a 475 question. What is, when you hear sampling frame, you think of, ooh, that's the people I what? So sampling frame and population are different. Good answers right there, Sophia. Great answers, Leo. You got this. Both of you 100 points. The sampling frame is everyone we have access to. So it's those we have access to in the population. Access of population. So do you think we have access to speak to anyone on an airline? I don't think we can do that. Do you think we have access, all passengers that fly this particular airline? Now that's a possibility. All passengers that flew this particular airline during the weeks they did the survey. And there's a typo. Who do you think is the people we could possibly speak to? So all passengers on that, well, so careful. Who could we possibly speak to? The people we could possibly speak to would be the people who flew during the time we did the survey. Would be the people who flew. Those are people we could possibly speak to. This is our what? This is our what? Barring any non-response bias. Barring any non-response bias, D is our what? D is our sample. The passengers on the 30 random selected flights are the people we did speak to. Theoretically speaking, the C are the people we could theoretically speak to. So I always love doing my Hodges Library example. So you go to Hodges Library. Hodges Library. At 2 p.m. What is your population of interest? You're right. What is your population of interest? What is your sample frame? What is your sample? Okay. So, and then we'll say, what is your parameter of interest? Okay. So I'm in Hodges right there. Katie, right there. Points. You go there at 2:30 p.m. What is your population? Shout out to everyone in Hodges. What up, Hodges Library? I'm weird. What is your population of interest? What is your population of interest, probably? Population of interest is going to be what? The population of interest will be what? Population of interest is going to be what? Students, UT students. There's like 20 of them. I love it. Students at UT. Whatever group you want to learn about. Does that make sense? Whatever group you're interested in learning about is the population of interest. So everyone at UT students, like the question would probably list it better, but the population of interest is the group you're trying to understand. So do I want to understand UT students? I do. I'm going to go to Hodges Library to talk to people. What is your sample frame? What is your sample frame? Now, this is theoretical. What is your sample frame? Seth. Great work there, Seth. Sample frame, exactly, and Marie and Seth, great answers, would be everyone who is in the library at this time. Because theoretically, you could what? Anyone who is in the library at this time, and this is why it's called the sample frame, because it's like a frame and that person's inside the frame. Theoretically, you could what that person. That's why it's called the sample frame, the ones you have access to. Theoretically, that person could be someone you could talk to. The sample frame is theoretical, and I think that's the harder question for a lot of people. It's the theoretical people you could talk to, not the people you do talk to. And the sample will be the students you get data from. So the ones who actually speak to you, that is your sample. The parameter of interest would be the what? Like, you have to expand on this a little bit, but the parameter of interest is the what. So the parameter of interest is the what I want to what about the population. Fill in the sentence. The parameter of interest will go for another 5-6 minutes here. I think there was one more. We'll be starting class here in 13. We'll go eat some lunch, breakfast, something. The parameter of interest is the what. What you're researching, what you want to understand. Great job, Maria and Seth right there. What you want to understand about the population. It's the kind of question you're asking. It's like the proportion of students with loans. And how do we gain insight into this? What is our sample statistic? Well, from this would be a categorical question. We could find out, good to see you here, Madeline. We could find out that in our sample, 40 out of 70 had, we'll do 60. 60 had loans. So the sample statistic here is actually what? The sample statistic is what right here? Like in notation. We're just doing a notation quiz here at the end of this. The sample statistic is actually what? Can you tell me the sample statistic? What is the sample statistic right here? The sample statistic, the sample statistic is what? Not mu. Good guess right there. It's not mu. The sample statistic, no, don't worry, good practice. It's P, close. This is X. This is N. It's 66%. And that is P hat. Great job there, CAD. Excellent work, CAD. That's P hat. So the sample statistic is our estimate of what? We don't want to understand from a sample of students how many had loans. We want to understand for all students the proportion that had loans. So what do you think we're trying to estimate? The value we're trying to estimate is what? The value we are trying to estimate is what? The value we're trying to estimate is what? In notation. The notation value we want to understand, the parameter of interest, which is the proportion of students have loans, is P. And what if I told you I could run the statistics on this in seconds? Like literally seconds. If you're wondering if I could actually run the statistics on this in seconds, it's taking me more to do this right here. Oh, really? It's prop test. And so now, there's the statistics. Seconds. We have to know, and this is what this class teaches, is when to do this. When do we need to do this? What does this output mean? I am 95% confident the true proportion of students with loans at UT is contained in the interval 53.2% to 78%. This is evidence for me that over 50% of students have students' loans by the p-value here, where I would reject the null hypothesis that 50% have loans. Now, we don't try to speak like statisticians a lot of times. We might say, the percent of students who have loans is probably somewhere between 53 to 78%. Does everyone see where I'm quoting these numbers? Because in my sample, I saw 66% of them had loans. So probably the true proportion, like for everybody at UT, is probably somewhere between 53 to 78. I've got about 95% confidence in that interval I just gave you. And also, that is good reason to believe that it's more than 50%. I mean, the interval's above 50. I don't think 50 is the truth. I'd also reject this right here. Could we make a normal curve for this data? We could. Let's hop over to jump super duper quick just to end off this. This is a gateway or a view into later. Let's go here to loans. It takes longer to do it in jump. And so we go to 40, 20, and then we go to, loans response. And yes, no, takes longer. It's just easier in jump sometimes. In R, sometimes there's the frequency, analyze, fit Y by X. Nope. Analyze, distribution, frequency. Wait. Frequency. Loan response there, and so it takes way longer. So much easier. Confidence interval is 95. There it is. I am 95% confident the true proportion of students with loans, and this one does chi-squared calculations, I think, is contained in the interval 54% to 77%. I found in my sample that 66.67% of them had students' loans. You're welcome. We'll be starting to hit the class soon. This is a peek into the future. This interval right here is trying to estimate the true proportion from our sample proportion found by 40 over 60. And this is for later test stuff. Colton, have a great weekend. I'll be responding more to questions. It is a busy day. With that, Tupabulu. I got invited to a 5-star raid and only 3 people showed up. I couldn't play that 5-star raid. I tried to do it this morning and couldn't play. We'll be back here soon. Have a great weekend if you're done. Starting up here soon. Class in just a moment. See you soon, everyone. Bye. Saying announcements. See you in class, everybody. If you want more review,